Okay, so in this lecture, the fourth lecture over chapter 10, alcohols and thiols, so this will look at how to synthesize alcohols by reduction, using metal hydride reducing agents and using H2 gas and some metal catalyst, and look at how to synthesize thiols as well. Okay, so again, one way to synthesize alcohols is by using metal hydride reducing agents, so we'll look at two. So we'll look at NaBH4 and we'll look at LiAlH4. So NaBH4 is what's called sodium borohydride. So BH3 is boron. So boron only has 3 valence electrons, right? It's in group 3 of the periodic table. So if you take BH3 and added H minus to it, then you would have BH4 minus borohydride. And the significance of this is basically a source of H minus, because the H that you just put on can come back off. So it's a source of H minus in reactions. So whenever you see NaBH4, you can just think of it as H minus. That's basically how it's going to react. So if you reacted that with an aldehyde or a ketone, so carbon's partial positive, hydrogen's negative. So they're going to react with each other. So you can take that lone pair on hydride, make a bond to this carbon, and if you make a bond, you can't put 5 bonds on carbon, so you have to break a bond. So the bond that gets broken is the weakest bond, the pi bond. So so break one of the C double bonds, O's. So now you have a CO single bond there. And oxygen now has 3 lone pairs because one of the pi bond, 2 electrons became a lone pair on oxygen, so that's negative. And so you added a hydrogen to carbon, and so what this is going to do then, it's going to take off a hydrogen from your solvent. So if you have a protic solvent, so partial positive hydrogen, so you can take a lone pair of electrons on oxygen, take that hydrogen, and the 2 electrons in the OH bond become a lone pair on carbon, on oxygen. And then that would be your major organic product. So basically you just take the C double bond O and reduce it to a single bond, to an alcohol. So you can do the same thing with LiAlH4. LiAlH4 is lithium aluminum hydride, sometimes just called LAH. So aluminum, just like boron, they're in the group 3 of the periodic table. So aluminum has 3 valence electrons. So H minus adds to aluminum, and now you have aluminum hydride. And so again, aluminum hydride is just a source of H minus, like BH4 is, because this H minus can come back off and go react with something else. So boron's got electronegativity of 2.0, and aluminum's 1.6, and hydrogen's 2.2. So if we looked at the BH bond, then H is negative charge density, right, and boron's positive charge. And because the electron density in aluminum hydrogen, or the electronegativity, is much bigger difference, so here the H minus is even more partial negative. So basically aluminum hydride is much more reactive than sodium borohydride is, but they're both just sources of H minus. So when you see LiAlH4, you can just think of that as being an H minus. So if we take the 2 electrons on hydrogen, make a bond to carbon, because that's carbon's partial positive, and break the double bond. So the hydrogen on carbon comes from LaH, or sodium borohydride, and then the hydrogen on oxygen comes from the second step. So then you do the second step, and O minus picks up a hydrogen, and now you have an alcohol. So basically in both cases, just take the C double bond O and make a COH, make an alcohol out of it. But recognizing the hydrogen on carbon comes from here, and the hydrogen on oxygen comes from the second step. Okay, so if we did the reduction of this molecule with sodium borohydride, so this is much less reactive. And it cannot reduce carboxylic acids, but this can. Same for esters. Sodium borohydride won't reduce esters or carboxylic acids. But it will reduce aldehydes and ketones. So again, this is just a source of H minus. So H minus is going to attack that carbon since it's partial positive, and that's going to become an O minus, which is going to pick up a hydrogen from methanol in the second step. So with sodium borohydride, you would make that as your product. But lithium aluminum hydride can reduce carboxylic acids and esters. So it will reduce them all down to alcohols. So the ketone is going to become an alcohol, and the carboxylic acid is going to become an alcohol. And the oxygen, the OH, will come off bonded to aluminum. Okay, so, but the point is, so that alcohol, since that carbon only has one carbon attached to it, it will become a primary alcohol. And that carbon, since it has two carbons attached to it, will become a secondary alcohol. Okay, so esters react similarly. So again, this is a source of H minus. So H minus, so take the lone pair of electrons on hydrogen. So if we just step through the mechanism, so it's similar to Grignard reactions and organolithium reactions with esters. So you would initially break the C double bond O. Right, and then you remake the C double bond O. So take a lone pair, remake the C double bond O, and kick off the conjugate base of the alcohol. Right, so now you have an aldehyde, and aldehydes react with lithium aluminum hydride. So as soon as you make that, it's going to react with another equivalent. So break the C double bond O again. And now you've added two hydrogens to that carbon, and now it doesn't have a leaving group, so now it's waiting for you to do the next step. So now you do the next step, H plus, in both the alcohol that left in the first step and the O minus that you just made are both going to pick up hydrogens. So technically you would need two equivalents of H plus. Okay, so this oxygen picks up a hydrogen and this oxygen picks up a hydrogen, and from the ester then you would make ethanol, and you would make that primary alcohol. So then esters are going to make two alcohols, and they're both going to be primary alcohols. Okay, so again, if we pay attention to the language of organic chemistry, notice in this reaction we use 1 and 2. We have to do those reactions in sequence. Whereas sodium borohydride, you don't, you can mix them all together. But with lithium aluminum hydride, we have to do them in sequence. If you don't do them in sequence, then that means you put everything in the flask together at the same time. And the problem with that is, well, H plus is going to react with H minus, and you're going to make H2 gas, which is flammable, and this is a very exothermic reaction. So if you threw everything in the flask at the same time together, it would probably explode. Well, probably explode on you, depending on the quantities involved, because of how exothermic reaction that is and how flammable H2 gas is. So when you do these reactions, you have to make sure you, for lithium aluminum hydride, you put LiAlH4 in the first step. and H plus in the second step, and because that's telling the chemist how to do this reaction. Okay, so you can also reduce C double bond O's by metal catalyzed hydrogenation. So you can take H2 and some metal catalyst. So you can add hydrogen across a C double bond O, just like in chapter 8 we looked that you can add hydrogen across a C double bond C. Works the same for C double bond O's. You just typically need a better catalyst. So something like rainy nickel. So this is just very finely divided nickel, so it has a very high surface area, and it's a very reactive catalyst. So in general, C double bond O's are harder to reduce than C double bond C's. So you would typically either need a better catalyst or you need higher temperatures and higher pressures. But then it's the same principle. You're going to add H and H across the C double bond O. And of course, you're going to add in this molecule, since you have an alkene, you're going to add hydrogen across the C double bond C as well. So you would make that, you would get rid of the alkene and you would get rid of the C double bond O, and you would add hydrogen across both. Okay, so if we did this reaction, then a ketone in this case becomes alcohol, right? Where you added those two hydrogens from there. Okay, so well, what if you have an alkene and a ketone or aldehyde and you don't want to reduce both? What if you want to keep the alkene? Well, you can't use H2 because the alkene is more reactive with H2 than the C double bond O, so it would react first anyway. So if you want to reduce the ketone or aldehyde and not the alkene, then you have to use the metal hydride. So that will reduce the C double bond O without reducing the C double bond C. And if you want to reduce both, then you can use the H2 and rainy nickel. And if you just want to reduce the C double bond C and not the C double bond O, then you can use H2 and a less reactive catalyst, something like palladium, and you would have to keep your temperature low. And keep the pressure of the H2 gas low, and then you should be able to reduce the C double bond C without reducing the C double bond O, especially if you follow the reaction closely so that you can stop it if you see the C double bond O starting to react. Okay, so if we want to synthesize thiols, then one way to do that would just be an SN2 reaction, like Na plus and SH minus. So we covered this in chapter 6, that this is a very good nucleophile. So this can do an SN2, take a lone pair of electrons on sulfur, make a bond to carbon, kick off bromine, and you've got the thiol, right? And sodium bromide side product. The downside to this reaction is that SH minus can be dangerous to work with because if it comes in contact with an acid. So if SH minus picks up an H plus, it becomes H2, which is a toxic, deadly gas. So that can be a hazard in lab to work with. Right, so SH minus, if it comes in contact with HCl, for example, then you make H2S. And so that's dangerous. So there is a safer alternative. Instead of working with SH minus, you could work with this compound thiourea. So it's a good source of sulfur, it's a good nucleophile. So the way that this reaction works, so sulfur can attack, let's go here, do an SN2, can attack carbon and kick off bromine. And so now you have this compound, and then let's take this and just draw a resonance structure. So take a lone pair of electrons, make a CN double bond, and take the pi electrons and make a lone pair on sulfur. Okay, and then the Br minus can take off a hydrogen from the nitrogen, And now you have that compound and HBr side product. Okay, now the hydroxide. So basically now you do the second step. So add hydroxide. So OH minus can attack there and break the pi bond. So make a lone pair on nitrogen. So now you have this. And then what we want to do is let's make a, sorry. Yeah. Okay, so let's take a lone pair on nitrogen, move it down to make a carbon nitrogen double bond and kick off the CH3S minus. And let's draw a resonance structure, make a carbon oxygen double bond, move those electrons up. Okay, and then now we have that, which that can take a hydrogen off of the HBr that you produced in the previous step. So now you have this, and then the SCH3 minus that you lost in the previous step can take the hydrogen from the oxygen. And now you have a urea side product. Now you have your thiol side product and a potassium bromide side product in this case. So that's a fairly complex mechanism, but predicting the product is easy. So this basically became SCH3SH, right? So it's just so this thiol-urea followed by the KOH with an alkyl halide is just a way to introduce SH into the molecule. So predicting the product is easy if you see that reaction. So that's the only time you'll see this reagent, thiol-urea. So if you see that, you should just recognize you're basically just going to lose a leaving group and put a SH there. So that would be your product. And then you would get the urea side product. And you would get KBr side product in this case, but that's the main interest. So wherever the leaving group is, just stick an SH there, and that's your product. Okay, let's take one more reaction here. So earlier in this lecture, we looked at how esters reduce. So if you took ester with lithium aluminum hydride, and again, if you just think of that as a source of H minus, and esters similar to Grignard with the LAH, similar to esters with Grignard reagents and organolithium reagents are always going to react twice. All right, so first one's going to come in, initially break the double bond. Right, but then you're going to remake the double bond. And in this case, the OR group is going to leave, but in this case, it's going to remain tethered to the molecule because of these CH2s in the back. So you're going to remake the double bond. Now you have an aldehyde there. O minus there. And now aldehydes react with lithium aluminum hydride, so another equivalent of hydride can react. So another H minus attacks there, break the double bond again. And then that's what you have after the first step. And so now it's ready for you to do the second step in the reaction. So now you add H plus, and again, technically you need two equivalents because you have two O minuses. So O minus picks up a hydrogen, this O minus picks up a hydrogen. And that would be your product. And so again, this can be, if you learn to recognize reactions, it makes your life in organic chemistry much easier. If you kind of just learn to see what's going to happen. So this is an ester with LAH. So you're just going to basically open that up there. And then this is going to become an alcohol. And then you're going to get an alcohol here as well. So alcohol, alcohol, and that's your product. So similar how Grignard reactions react, right? So if this was a Grignard reaction instead, so you're just going to take basically 2 of these and put them, well, let's do this better. So 2 of these are going to go here. You're going to unzip that, and this is going to become an OH, and this is going to become an OH. So that C double bond O becomes an OH. You add 2 Grignard reagents. And the oxygen of the ester OR group becomes an OH, and that would be your final product. So very similar, right? Here you just added 2 R groups from the Grignard reagent, and here you added 2 hydrogens from the lithium aluminum hydride. And in both cases, you cleave the C double bond O bond and open that up. Of course, if it was an ester like this, where it's not cyclic, and you did the reaction, the same basic concept. Right, you're going to cleave that, and so this will become an alcohol, and this will become an alcohol, and 2 of these will attach to that carbon. So you would get alcohol there, 2 Grignard reagents attached to that carbon that used to be the C double bond O, and this alcohol left and becomes that. They're just not tethered in this case to each other like they are here because it's not cyclic to begin with. Okay, we'll stop there.